In this screencast I'm looking at L'Hopital's rule, and I'm going to illustrate its use to evaluate the limit in two separate examples. I've put the rule up here for you. It's used to evaluate the limit of a quotient, f of x over g of x, in the limit as x tends to little a. And it works if the limits individually of f of x and g of x are both 0, or are both infinity, or are both minus infinity. And then, as long as the limit of f primed of x over g primed of x exists, that is the answer to the problem, to the original limit. Although it may be the case that we have to do this rule more than once, as you'll see in the first example I've got for you. So let me write the first example out. Let's say we are asked to evaluate the limit as x tends to infinity of x squared e to the minus x. Well, the first thing I would notice is that we don't actually have a quotient here. So what I'm going to do first of all is rewrite the problem so that we do have a quotient. So x squared e to the minus x can be written as x squared over e to the x. And there's my quotient. So what I now have to check is that it's applicable to use L'Hopital's rule, and the limit of both x squared and e to the x, as x tends to infinity, that the limit is infinity in both cases. So therefore I can apply L'Hopital's rule, and what I have to do is differentiate top and bottom separately. That's important. We're not using the quotient rule to differentiate here. We have the numerator differentiated, which is 2x, and the denominator differentiated, which stays the same. And if I now try to evaluate the limit, you can see that I still have infinity in the numerator and infinity in the denominator. So that just means I have to apply L'Hopital's rule again and differentiate again, top and bottom separately. Now I'm in the position where I can evaluate the limit immediately, because as x tends to infinity, the limit of 2 divided by e to the x is just 0. So that's the answer to this first problem. I'm now going to move on to the second problem, and here I'm going to evaluate the limit as x tends to 0 of e to the 3x minus 5x all to the 1 over x. And if I look at that question, to me there are two things that strike me about it. First of all, I don't have a quotient. But secondly, that exponent, the 1 over x, is a little bit nasty. So my thoughts here are, first of all, to define f of x to be the thing that we want to find the limit of eventually. But then, if I take the log of f of x, I can deal with that exponent. So what I'm going to do is define g of x to be the log of f of x. And if I log f of x, the 1 over x comes down in front. And I hope you can see that I've actually killed two birds with one stone here. I've now ended up with a quotient, as well as getting rid of that 1 over x in the exponent. So what I'm now going to do is find the limit as x tends to 0 of g of x. And after I've done that, I'll look at how I can use that to find the limit of f of x. So what I have here is a quotient, ln of e to the 3x minus 5x all over x. And let's check it's in the right form. In the numerator, I have ln of 1 minus 0, ln of 1, which is 0, and in the denominator I've got 0. So at the moment this is 0 over 0, and therefore I can apply L'Hopital's rule. Let me do that now, and I'm going to differentiate top and bottom separately. The denominator x, if I differentiate that I get 1, so in fact that's not actually going to affect things at all. But let me differentiate the numerator. The log of something is 1 over the something multiplied by the derivative of the something. That's the chain rule. So that's the derivative of the numerator, and I divide by the derivative of the denominator x, which is just 1. And now, can I evaluate that limit immediately? And I think I can. When x is 0, I have 3 minus 5 minus 2 on the top, divided by 1, all divided by 1. So the answer there is minus 2. And that is the limit of g of x as x tends to 0. And what I'm now going to do is remember the link between g and f. It's actually the limit of f of x that I want, and f of x is e to the g of x. So, when I want the limit as x tends to 0 of f of x, I remember that f of x is e to the g of x. And now what I do is use continuity of the exponential function. So, in fact, I'm wanting e to the limit as x tends to 0 of g of x. And that limit is the limit I've just found. So I'm done. I get e to the minus 2. And that's the end of the solution to this second problem.